Welcome everyone. My name is Magsam. I'm a computer vision scientist at Visikol, and today I'm going to talk about detecting tumor regions using convolutional neural networks. In this video, we are going to go through the following topics. First, we will introduce the motivation for pursuing this type of project. Next, we will describe a very influential dataset that was released in 2016. Then, we will cover a general approach Visikol uses for many of its digital pathology-based projects. Going forward, we will summarize the implementation and training results of our convolutional neural network used in this project. And then, we will visualize the results of our predictions on 2 test cases of whole slide images. And finally, we will end with some concluding remarks. The motivation for this work stems from a very important element of breast cancer, which is metastasis. The treatment plan for breast cancer can vary significantly based on whether the cancer has metastasized or not. One of the most widely used methods of determining metastasis is to analyze a biopsy from the sentinel lymph nodes. This is performed by a pathologist who will look over H&E tissue sections of the sentinel lymph node. While this method is very useful at determining metastasis, it can often be time-consuming and small tumor regions can often be overlooked by mistake. Therefore, the research community and Visikol has taken to working on novel approaches to aid pathologists using computer vision and deep learning. The data we used in this project is from the Camelyon Challenge. The Camelyon Challenge was organized in 2016 by the Diagnostic Image Analysis Group and Department of Pathology at the Radboud University Medical Center. Its purpose was for researchers to come up with new algorithms to accomplish the following 2 tasks. First, to automatically determine a probability that a given lymph node tissue is cancerous, and 2, predict tumor regions in the whole slide image of the lymph node tissue. The dataset consists of almost 1,400 whole slide images from 5 different medical centers in the Netherlands. These images were acquired at 0.23 to 0.25 microns from several different scanners. Here's one of the many approaches we take in a deep learning project for digital pathology. First, we separate each whole slide image into smaller image patches. This is because each whole slide image is extremely large, and therefore it would not be feasible to train a neural network with such a large input. Next, we train an image classifier using a convolutional neural network. Third, we evaluate the performance of our classifier on test data that has never been seen by the neural network. And lastly, we perform inference on a whole slide image using the trained convolutional neural network using a sliding window approach similar to the animation seen on the right side of the screen. As mentioned before, we need to break up the full-size whole slide images into smaller image patches. Therefore, we utilize an open-source version of the Camelyon dataset that has already been pre-processed using the raw data provided by the organizers. There are roughly 330,000 images with sizes 96 pixels wide by 96 pixels high, sampled at 10x magnification. Each image patch has an associated label for training. An image is labeled as metastasis if the center 32 by 32 pixel region contains at least 1 pixel of tumor tissue. If there are no tumor pixels in the center region of the image, it is labeled as healthy. At the bottom of the slide, you can see a table of the distribution of training, validation, and testing images. Here are some examples of the images in the patch Camelyon dataset. The top row shows 5 examples of images that belong to the metastasis class, while the bottom row shows images that belong to the healthy class. As you can see, there's a large amount of variation between images due to different staining intensities, amount of background, or the shapes of nuclei. We utilize the CNN architecture MobileNet v2, which is a parameter-efficient architecture and features significantly less computations compared to some of the deeper architectures such as the ResNet or VGG variants. We use a binary cross-entropy loss function during training. What this loss function does is help update the parameters of the neural network by penalizing wrong predictions. There's a component to penalize false positives and a component to penalize false negatives. During training, we seek to minimize the value of this loss function by continuously updating the parameters of our network using gradient descent over a large number of iterations. After training our neural network for over 30,000 iterations and monitoring the loss function of training data and validation data, we test our trained model on the test data. Remember, the test data has never been seen by the network and thus is a good approximation of how well the network can generalize to new data it has not seen before. We reach an accuracy of almost 90%, a precision of 0.64, recall 0.61, F1 0.62, and specificity of 0.84. Each of these metrics can be used to evaluate different aspects of our network, where it is excelling and where its pitfalls are. Another useful tool we can use to understand the performance of our network is a confusion matrix. On the y-axis, we have the ground truth labels, and on the x-axis, we have the prediction labels. So we can see that we have correctly classified 90% of the healthy test samples and 88% of the metastasis samples. And we wrongly predicted 10% of the healthy samples as metastasis and 12% of the metastasis samples as healthy. This means that our trained network is slightly better at classifying healthy samples with a lower number of false positives. This is reflected by our precision score, which is higher than the recall score. Now we are finally ready to test our trained network for whole slide prediction. Our network expects small image patches 96 pixels wide by 96 pixels high as input. Therefore, we break up the whole slide image into many small image patches and classify them using our trained neural network. Then we reorganize the predictions into the same shape as our original whole slide image to visualize our results. The final result is referred to as a probability map because the output of our neural network is a continuous number between 0 or 1, where a value closer to 1 indicates a higher probability of belonging to the metastasis class. In this case, the yellow regions represent high probability of belonging to the metastasis class, while blue and purple represent the healthy class. So as you can see, our trained network performs very well on this test case, correctly identifying tumor regions with respect to the ground truth annotations on the right. The bright yellow regions with the green arrows showed tumor regions that were predicted in an automated fashion using our trained neural network. Here's another test case for whole slide prediction. As you can see, our network does a good job of predicting both small and large tumor regions in the tissue as shown by the bright yellow spots and green arrows. You'll notice there are some very small bright yellow spots scattered throughout some healthy tissue. These would be considered false positives since they are not associated with a tumor region in the ground truth annotation. To fix this, we would retrain our network using a modified loss function where we penalize false positive predictions more than false negatives. This would ensure a low false positive rate during testing time. We could also do the same thing if we were more concerned with false negatives. However, for this demonstration, we equally penalize both wrong forms of prediction for simplicity. In this video, we first discussed the significance of breast cancer metastasis and how it can drastically change prognosis and treatment plans. This creates a need to accurately identify metastases to ensure best overall care for the patient. A pathologist uses tissue biopsies of sentinel lymph nodes to detect metastases, which is time-consuming and can oftentimes be riddled with inaccuracies. We believe that a deep learning technology such as this presented in the video would prove to be largely beneficial in combination with a pathologist to improve metastases detection and speed up manual evaluations. Thank you all for taking the time to learn about an important research project we continue to work on here at Visikol and some of the technologies we incorporate in many of our digital pathology services. We hope to have you back for more for any of our future video series.